In this video, we're going to take up all the questions from relative velocity. Starting off with question number 1, what is the meaning of OM and G? As from our notes, that's what OM and GLs represent. Let's go through an example. All right. For example, let's say we have an airplane. An airplane is flying, in the air. So here are clouds, and the air has a moving air current relative to the Earth itself. So the Earth itself is the ground. The air may be moving, and that's the medium. And then we have the plane, which is the object. If we know how fast the airplane's flying relative to the air current speed, then this is the velocity of the object relative to the medium. All right, so the plane could be flying at, I don't know, Mach 1, let's say, relative to the air. But the air is normally not static, it's often in motion, so we have another vector involved, which is the velocity of the air, or velocity of the medium, relative to the ground. So if at the end of the day we want to figure out what the end result vector is, so VOG, then we need to add VOM plus VMG. And as a reminder, you know that you're setting up this equation properly when adjacent subscript letters are the same, and whatever that's left over describes the resultant vector. That's how you know you set it up properly. As you are adding vectors, yes, they are commutative, so you can technically flip them around, but once you start doing that in these problems here, you might start making mistakes elsewhere. All right, so we're just going to ignore this commutative property when we're answering all the homework questions, just to stick with one consistent standard. All right, let's move on to question number 2. A plane is flying, and you can either walk in the same direction that the plane is flying at, making your velocity relative to the ground faster, or you could be walking backwards, back to where the washrooms are in the plane. First off, we should make an assumption, all right, of direction, so north being positive. Then we can treat all the vectors as scalar, and this will save us a lot of time in solving our problems. All right, so the plane is flying in the positive direction, and you two are also moving in the positive direction. Then yes, the sum of your two values will be much higher. So your velocity of the object relative to the ground, is that correct? No. Ooh, this is typo. That's VOM. There you go. It's typo here. Okay, so VOG is equal to VOM plus VMG, and wow, no, that's correct. Medium to ground, sorry, VMG. VMG, sorry about that. Didn't notice that typo beforehand. Alright, so VOG is equal to VOM plus VMG. Double check, make sure that adjacent subscript letters are the same, and whatever that's left over describes the overall story. And then from there you can move onwards. So 1.5 kilometers per hour plus 100 kilometers per hour will give you 101.5 kilometers per hour. As we're adding, we should look at the measurement that's least precise. So this one's assumed to be measured to the nearest whole, so we should also round to the nearest whole as well. 102 kilometers per hour, and this is towards the north as a vector. And if you're going in the opposite direction of the plane's flight, then yes, there will be a difference in value, and your overall speed relative, or your velocity relative to the ground, will be less. So VOM plus VMG, and this time around is negative 1.5 kilometers per hour plus 100 kilometers per hour, which will initially give us 98.5 kilometers per hour. As we're rounding to the nearest whole number, I know a lot of us will be tempted to round up to 99, but technically, as you're at the exact midpoint, 98 kilometers per hour would be the grammatically correct answer. Of course, on a test, if you give me 99 kilometers per hour, I'm okay with that because I know you're under pressure there. Okay, so I'm not going to worry too much about that. And at the end of the day, if you look at the difference between these two, it's an error of about 1%. And given that these values are two significant figures, that's expected. So either number is still acceptable anyways. Question number 3, there are 4 parts to it, and we'll start with number 1. Both are heading in the same direction. And yeah, I'll do a little sketch. Okay, if we take it that to the right is our positive direction of travel, car A is behind car B. but car A is traveling a lot faster. So car A is traveling a lot faster and car B is traveling quite a bit slower. Starting off with our givens, I hope this part over here makes sense, but there's also this other subset of givens, and let me just explain what this is all about. Let's say that you're walking. There you go. Yeah, awesome. Okay, you're walking. I'm not an artist. And as you walk, let's say towards the right, you'll notice that the ground sees you traveling in the opposite direction. Right? If you look down to the ground appears to be moving backwards relative to you. So that's what I want to get through with these positive and negative meanings of a similar vector. Right? So this is the velocity of car A relative to the ground. So the car A is moving in the positive direction, but the ground appears to be moving backwards. Okay, so all I did was I just flipped the letters around, and as a consequence, the perception of what's going on flips around as well. Okay, now we can go back to our generic equation. Velocity of the object to the ground. Oh wait, in this case over here, it's A behind B in reference to B. So velocity of car B relative to car A. That's what we're trying to look for at the end of the day. That's equal to two smaller vectors. As a reminder, adjacent subscript letters should be the same, and whatever that's left over describes BA. So we know that this has to be B and the last part has to be A, and the only thing that ties these worlds together is the ground itself. And that's how we got VBG plus VGA. Okay, velocity of B relative to A. Velocity of B relative to G is equal to 45 kilometers per hour. And VGA, as we have from up here, is equal to negative 80 kilometers per hour. That will give us a difference of negative 35 kilometers per hour. After all, if car A is traveling a lot faster than car B appears to be moving backwards, right, from the perspective of car A. So as you're moving quickly ahead, the slow-going car is approaching closer and closer towards you at negative 35 kilometers per hour. For the next part over here, this time around it's VAB. Okay, how fast is car A traveling relative to car B? So VAG plus VGB. All right, AG is equal to 80 kilometers per hour, and GB is equal to negative 45 kilometers per hour. That will give us positive 35 kilometers per hour. And this is from the perspective of car B. So as car B is slowly trotting along, car A passes towards it, all right, in the positive direction of positive 35 kilometers per hour. Okay, third part. Both cars are heading towards each other, and you need to have a frame of reference. All right, so we'll take it that car A is traveling in the positive direction, meaning that car B must be moving in the negative direction. And we also got to fix up the symbol over here as well. That negative will become positive. Okay, with those givens, and we know that the standard formula is, what is it, V relative to A, so VBA is for this one. That's equal to VBG plus VGA. BG is negative 45 kilometers per hour plus VGA, which is negative 80 kilometers per hour, and that gives us negative 125 kilometers per hour. And for the last one, we're just doing velocity of car A relative to car B. B is the frame of reference, so speed of A relative to B. That's VAG plus VGA. Whoops, VGB. AG is at 80 kilometers per hour. GB is at positive 45 kilometers per hour, and that's equal to 125 kilometers per hour. Once again, if you need a picture just to see what's going on, here's car A traveling this way, and here's car B traveling that way. Here's my awesome looking cars. Okay, so the first one is relative to car A. If we take that this is the positive direction, then yeah, car B seems to be screaming back at you backwards at a crazy fast speed. All right, and we take it that car B is the frame of reference, and I think I had to change all the signs now. Whoopsie daisy. So if the B's frame of reference is positive, then this would have been positive and this would have been negative, and what is it? This would have been positive and this would have been negative. Whoopsie daisy, I forgot to do that. So AG is at negative 80 kilometers per hour and GB is at negative 45. So whoopsie daisy, forgot about that minus sign there. Good thing I double checked. Okay, so to car B, if you're taking this way as positive, then yeah, car A is screaming towards it in the opposite direction of 125 kilometers per hour. So that's how you make sense of the plus minus signs. Number 4, now we are dealing with non-collinear vectors, or vectors that are not parallel, and it does help to draw a sketch out. All right, and the sketch doesn't have to be perfect to the scale, but approximately. All right, and that'll help guide you in figuring out what the answer should roughly be at. Okay, so the airplane's flying this way if we assume that to the top of the page is north. Okay, the wind is blowing towards the south, and it's about 1/3 of the length. So that's what approximately should be. We are adding these two vectors together from head to tail, so our resultant vector would be this one over here. Now my advice to you is that when you draw your resultant vector, either you color code it out, or if you do in black and white, just do it as a nice big bold line. That way you can see all the components that give you to your final answer of VAG. Okay, so I'll make this bold too, VAG, just so you know that this is the resultant vector. All right, it's very similar to how you would deal with displacement. For example, in our previous lesson, delta dr is equal to delta d1 plus delta d2, plus so on and so forth if you have more to add with it. Except that here we're not dealing with displacement, we're dealing with velocity. Whoops, equals. Okay, we're dealing with velocity, so velocity of A relative to G is equal to V A medium, or the medium here is the wind, plus V, the medium, to the ground. Okay, and you can see we're following the correct format. AW is the first vector, WG is the second vector, and we're trying to look for the resultant vector. In this case over here, our resultant vector is our relative velocity. So we have everything all set up nice and well. In this question over here, I always like to start off with easier questions first. You'll notice that this is a special type of triangle. It's a right triangle. So with a right triangle, we don't have to go through all the crazy complex ways of component method or trig method. I mean, if you want to go through it that way, you can. Take this as 90 degrees and work away through it, and it will get you to the correct answer. All right. But knowing that this is something that Pythagoras can solve, let's just use that method instead. Okay. So VAG as a scalar, that's the hypotenuse, will be equal to VAW plus VWG squared. Again, this only works because this is a right triangle. In any other case, we wouldn't be able to solve it using such a simple method. Okay, so the magnitude of AG is equal to the root of AW, which is 120 kilometers per hour squared. Again, we don't need to deal with vectors when we deal with Pythagorean, because that will just wreck things. All right, and after all, Pythagorean, you can't tell the angle. Okay, we're using Pythagorean theorem. It will only tell you the length of the hypotenuse, and that's it. So that's another reason why we drop the units. Pull out our handy dandy calculator. Come on, calculator. Where are you? There you go. All right, so we have, whoa, what happened here? That was the strangest thing. Okay. I'm recording this real time, so I'm just going to let all the mistakes be as they are. Okay, square root. Luckily, this calculator opens brackets for me automatically. Many don't, so just watch out for that. 120 squared plus 40 squared. And you know that with regards to these triangles over here, the hypotenuse will always be longer than your longest side. So you know your final answer is going to be greater than 120. If you get any answer less than 120, you know you made a mistake. Yeah, that sounds about right. It should be greater than 120, so 126.49. If you're wondering how many sig figs should you carry, I am going a little bit overkill over here, but in general, you want to carry at least one extra sig fig compared to your at least certain answer. So you'll see that the 120 here is 3 sig fig and the 40 is at 2 sig fig. So you should really add one more giving you 3 sig fig. I always like to do 4, and 5 is a little unnecessary, but that's okay. We'll just keep it there for now. Alright, next thing is we need to find out the angle over here. And if we look at the relationship in this triangle over here, we have the opposite and the answer of the adjacent. Okay, so since we have the opposite and adjacent, and yes, we do have the hypotenuse, but this is rounded. Alright, so we don't want to be recycling that as it's approximated. I'll stick with black and white. Theta is equal to, therefore, opposite and adjacent, that's a tan inverse, of our opposite, which is VWG, over VAW. Now, VWG is equal to 40 kilometers per hour divided by 120 kilometers per hour. You could calculate it like this, and some of you smarty pants might notice that you could also do this at tan negative 1 of 1 to 3 ratio. Okay. Most important thing here is to make sure that these units are the same, because if they're the same, they will divide each other out to 1. Okay, so you can't be dividing kilometers per hour by miles per hour. Okay, you can't. That will not work out. All right, because you're not going to get a ratio. With regards to sine, cosine, and tangent, at the end of the day, it doesn't care about how big or how small your triangles scale out to. It's really the relationship between the side lengths. All right, so a 40 to 120 ratio is the same thing as a 4 to 12 ratio, which is the same as a 1 to 3 ratio. All right, and your calculator will spit out the same answer in all of those cases. Don't believe me? Go ahead and take out your calculator and try it out. Come on, calculator. There you go. Okay, so shift tan of 40 over 120 will give you the same answer as shift tan of 1 to 3 ratio. It'll be the same exact answer. Okay, 18.43. Okay, so since all we're concerned about is the velocity, which is a vector, and therefore your velocity of A relative to the ground as a vector is equal to 2 sig fig, which is 1.3 times 10 to the 2 kilometers per hour, and from the east, 2 sig fig is 18 degrees towards the south. There it is for part A. For part B, since we know the physical length between these two, which is not the same diagram, but you just know that it's going to be in the same direction, that is your displacement. All right, so you know that your displacement from the airplane's beginning, I guess, to the ground, I'll just call it delta D. Okay, that's equal to 1,000 kilometers, and your velocity of air to the ground is equal to 1 to 6.49. All right, if you're planning on reusing the numbers, carry some extra sig fig. Don't use the rounded one, otherwise your final answer will be further rounded from what the correct answer should be. Okay, so yeah, I'm carrying 5 sig fig. You can try this out at 4 sig fig, and it'll still round to the same correct answer. All right, when you round down to 2 sig fig. Anyways, we'll stick with this as our givens. And we know that from our most generic of kinematic equations, velocity is equal to displacement over time. So we try to isolate for time, and time is equal to displacement over velocity. So 1,000 kilometers divided by 1 to 6.49 kilometers per hour. Kilometers divided by kilometers per hour will give you hours, and the rest of it, we just need our calculator for this. So 1,000 divided by 1 to 6.49, and we'll get 7.9 hours. Two significant figures. Nice. A boat wishes to travel east. Since this is our resultant vector, make it nice and bold. All right. If you want to color code it, sure, color code in green. Otherwise, just take your pen out and make it nice and thick. All right. So this is our final answer at the end of the day. How is it influenced? In this case over here, it's because of this river current that is flowing towards the north. Okay, so we have a river current flowing 10 kilometers towards the north. Now let's say that we innocently try to paddle our boat towards the east. We know that if we travel towards the east and the water current brings us towards the north, then we know that our end result vector will be pointing somewhere out here. But that's not what we're trying to look for, right? We want our end result to be facing towards the east. So the only way to allow that to happen is that if we fight against the water current. So if the water current's traveling towards the north, we know that we need to force ourselves towards the south so that when the water current draws us up, we end up traveling towards the east. And that's how we will structure our triangle over here. Okay, and luckily for us, this is a nice right triangle, so it's easier to solve. There you go, all animated out. Okay, and before we move on, let's just write out the generic formula. Velocity of, what are we doing? Boat to the ground is equal to the velocity of the boat to the water plus the velocity of the water to the ground. All right, and this is the check you want to do. Adjacent subscript letters the same? Yep. Leftover letters describing our end result? Yep. All is well. Okay, so we know that our formula is written out correctly here. Does our diagram match up with our equation? VBG is our resultant vector. Yes, it is. And it's based upon vector number 1 plus vector number 2. Okay, so that's a good check that we should do every single time before we move on. Because if you set up your triangle incorrectly, you're obviously not going to get the correct answer. Okay, so we did the formula check and we did the diagram check. And now we can move on. Questions 1 through 6 are fairly straightforward in the sense that we're only dealing with right-angled triangles, right? And questions 7 and beyond deal with all the other types of triangles that exist, so we'll have to start pulling out all our trig techniques. Okay. First off, what are we trying to look for? Oh, we're trying to look for how does everyone see the boat traveling. Okay, so the boat seems to be traveling, or pointing at least, at this angle over here. So let's figure out that angle. Okay, velocity of the boat as seen by the person on the shore. Oh wait, no, we're trying to look for this one. Sorry, we're trying to look for that one. Okay. Okay, so what do we know so far? VW is at 30 kilometers per hour. VWG is at 10 kilometers per hour. So we know the opposite and we know the hypotenuse. All right. With that, we can figure out the angle they must, the heading, yep, the angle they must be traveling at. So let's do that first. Opposite, hypotenuse, to find that out, or the angle of that, we use sine inverse. Our opposite in this case over here is VWG, and our hypotenuse is VBW. WG is at 10 kilometers per hour. VW is at 30 kilometers per hour. And again, make sure that the units are the same because they need to divide each other out. Right? Divide to 1. So you could type in your calculator the sine inverse of a 1 to 3 ratio and it will give you the same answer. All right, so shift sine of 1 to 3 and that will give you 19.5 degrees. I'll just write down 47 just to carry some extra sig fig in case if we need it later on. Okay, so that's the heading of the boat. The boat has to head 19.47. So if we want to write out our VBW, the boat to the water is at 30 kilometers per hour east, facing at 19 degrees south. And if we want to find out our VBG, well, we know that the boat wishes to travel east. The only thing we're trying to solve for now is how many kilometers per hour is it traveling towards the east. Okay. I'm just trying to think of how I'd solve this. You could use trig. I think I'm just going to use a Pythagorean theorem. Okay. We know the hypotenuse of VBW is equal to VBG plus VWG squared, and we're trying to look for VBG. That's equal to VBW squared minus VWG squared, square rooted. Okay, BW, and yeah, you hope that's larger, otherwise your calculator will not give you a correct answer. Remember to square that, subtract 10 kilometers per hour squared. Calculator time, square root of 30 squared minus 100 gives us 28.28 kilometers per hour. So the velocity of the boat to the ground is therefore equal to 28. Oh, I can write it over here. 28 kilometers per hour. So VBG is equal to 28 kilometers per hour towards the east. Okay, and that's how the people on land see the boat traveling at. So it's not traveling as quickly because the boat unfortunately had to fight against the weather current. So it dropped from 30 as its nautical speed, I guess, down to its land speed. All right, for the case of the wind blowing from the east, and if you remember the rules in geography is that, for example, the easterly trade winds, right? When you have a globe over here, the winds that were commonly used towards delivering stuff from the Europe and Asia and whatnot to North America. I know I'm not the best of artists, but there you go. They dealt with these trade winds that look like this, and they're called the easterly trade winds, all right, or the northeasterly trade winds. In other words, winds are always described from where they're coming from, all right, so that's why I underlined from the east. This reminds us that the wind has to be blowing towards the south. Okay, so in our little sketch, if you want to draw one out, the wind is blowing towards the south. If you take it that north is positive. Okay, so the wind is blowing towards the south 80 kilometers per hour, and the plane is flying at 200 kilometers per hour. Find the velocity of the plane relative to the ground if the pilot points the plane towards the north. So the plane is flying this way, but is fighting against the air current. What's going to happen? Do I have a sketch for this? Ah, east. I mean, I drew it wrong. Oopsie daisy. Okay, I'm sorry. I wasn't reading carefully. Okay, it was from the east. That means blowing towards the west. Yeah, so there you go. Okay, the wind is blowing towards the west. I apologize for that. Okay, so the wind is blowing towards the west, and the plane flies towards the north. We know that at the end, our resultant vector would look like that. And that's how we draw the sketch out. Okay, so yeah, the wind is blowing from the east. In other words, it's traveling towards the west, and the plane is trying to blow towards the north. When you add them together, what is your resultant vector? That's what we're trying to solve for. Okay, I have that animated out. Another lovely right triangle. So VPG for right angle triangle, we can use the Pythagorean theorem. VPG is equal to VWG squared plus VPW squared. VWG is equal to 80 kilometers per hour squared plus our 200 kilometers per hour squared. So the root of 80 squared plus 200 squared gives us an answer greater than our highest side of the triangle. After all, it's a hypotenuse, so yeah, 215 sounds about right. 215.4 kilometers per hour. Okay, so that's our VPG as a magnitude. That's all that Pythagorean theorem can ever tell you. If we need to make it to a vector, we need to find out the angle down here. I would strongly advise you not to use VPG as the measurement that you use. After all, there's rounding error in it. So that's why we're going to use these two values to try to find out our corresponding angle. And that corresponds to the tan inverse of our opposite over our adjacent. Opposite of VWG at 80 kilometers per hour divided by our 200 kilometers per hour, which is equal to the shift tan inverse of, you could do 8 over 20. That would work out as the same, of 21.8 degrees. Okay, so our final statement, VPG, because it is a vector, right? It has an arrow on top. I actually was too arrogant when I was in university, and I forgot about the whole thing that vectors include direction, and I thought I aced 100% on my midterm exam. Instead, I didn't ace it. I lost quite a few marks because I forgot to include the angle. All right, so please watch out for that. I want you guys to ace your future tests as well. That's why I'm going through the effort of making these videos. North 21.8 degrees towards the west here. And if we want to round this properly, which I wasn't paying attention to, 2 sig vig, yeah, 2 sig vig, so this would be 2.2 that will round up to 2.2 times 10 to the 2 kilometers per hour, north 22 degrees towards the west. And that will be my answer. Now, you could also calculate it out in meters per second. That's up to you. Just divide by 3.6 on your calculator. Whoops, wrong button. Oh well, you get the idea. Okay, the second one, here's where things get a bit more challenging because the pilot wants to fly towards the north. In other words, we want this to be our final vector, okay? Nice and thick towards the north. We know that we're fighting against crosswinds that look like this. So how should we attach them? Okay, you know that if you try to fly north, you're going to end up somewhere over here. So in order to make this happen, you got to kind of fight against the wind current to allow the wind current to drag you back onto the course that you're intended to go for. So your triangle should look something like this, and I probably have that all animated out. Yep, nice and clean like so. Okay. All right, what do we know so far? We know that this is still 80 and this is still at 200 kilometers per hour. And if we're trying to find out the velocity of the plane relative to the ground, well, we already know the first part, which is the direction, right? VPG, even though we don't know the magnitude, we know that has to face towards the north. Okay, and again, since this is a lovely right angle triangle, we can use our whole c squared is equal to a squared plus b squared. Just make sure that you label your vertices correctly. So this would be your c, and we'll take, I guess this as a and this as b. Okay. All right, so c squared, what are we trying to look for? We're trying to look for this, which is b. So yeah, I'll just rearrange first. B squared is equal to c squared minus a squared, or that is equal to 200 kilometers per hour squared minus 80 kilometers per hour. If you decide to use this formula here, make sure that you label your vertices. All right, otherwise the reader has no idea what you're defining as A, B, and C. Okay, so draw a sketch, factor that in, and then you can skip out on the whole V, P, W, W, G, and all that other crazy business. Handy dandy calculator. Root of 200 squared minus 80 squared, 183. Yeah, the VPG should be shorter than the hypotenuse, definitely. Rounding to 2 sig fig, then I would have 1.8 times 10 to the 2 kilometers per hour for that one. Okay, and if you want to take out your calculator and divide by 3.6 to convert into meters per second, sure you can, and that's how you get to your 51 meters per second if you wanted in meters per second. On a test it doesn't matter because the question never asked about, you know, what the velocity should be. It should be measured in, you know, meters per second, kilometers per hour. It doesn't matter. They're both correct. Okay, so the third one's going to be a bit more challenging, okay, because the third one is the plane is trying to fly at an angle. Okay, so the plane is flying at north 20 degrees towards the west. The wind is still blowing towards the west. So if you connect it like this, then you know that your resultant vector would look like that. And it's up to you how you decide to solve this problem here. You can solve it by using component method or by trigonometric method. It doesn't matter. They're both of, I'd say, the same difficulty. Okay. So to buy myself some more space in solving that question, I need to erase all of these and just start from over here. Okay, what do we know? We know that in our givens, that the velocity of the plane to the wind is at 200 kilometers per hour north 20 degrees west, and the velocity of the wind to the ground is at 80 kilometers per hour towards the west. And we're trying to look for VPG. That's our question mark. Totally up to you if you decide to solve by component or by trig. I'm just going to stick with component here. Okay, so to help me out, I'm just going to draw the sketch one more time in black and white. And the reason why I want to do it in black and white is that I want to break down these into their components. So in other words, this vector over here of the plane to the wind has its own horizontal and vertical components, and this would be and an angle of 20 degrees. All right, and then the second one only has a horizontal component. Okay, so let's first start off by writing out the formula. So VPG is equal to VPG in the x, VPW, plus VWG. There you go. Adjacent, same. Leftovers, big story. Yeah, sounds about good. Sounds about right. Okay, so first off, we're going to solve this in the x dimension. Okay, so VPGX is equal to VPW in the x dimension, which is right over here. We know the magnitude is 200. Do that in black and white. So VPGX is equal to our 200 kilometers per hour times, this is the opposite, right? So times the sine of 20 degrees. Yeah, it's 20 degrees. Another thing is that if you take it that east is positive and towards the north as positive, then this should be a minus sign here. Okay. We're going to add it to the second vector where, again, 80 kilometers per hour towards the west is negative 80 kilometers per hour. Calculator out. So negative 200 times the sine of 20. This calculator open brackets, so make sure you close bracket it, otherwise it's gonna add the 80 or subtract the 80 from the angle and not from the final measure. So plus negative 80, or you could just subtract 80 if you want to. All right, and you get negative 148.4. Sure, just carrying one extra sig fig just for good measure. Kilometers per hour. That's our VPGX. Rinse and repeat in the y dimension. So VPGY is equal to VPWY plus VWG in the y dimension. And yeah, just for good measure, I'll just write it out here one more time. VPGX is equal to VPWX plus VWG in the x dimension. Okay. I kind of just recycled my generic formula. So there you go. And these are vectors, but I'm going to quickly convert it to scalar, assuming that north is positive. Okay, so VPWY works out to in the north direction, so it's positive 200 kilometers per hour times the cosine of 20 degrees plus 0 kilometers per hour. I mean, you could have also done that as well to save yourself some time. Either way, you just need to tell the reader why is it going to 0. Okay, why did this term disappear? Okay, so you can either slash it out and get rid of this, or just write down plus 0 kilometers per hour, so the reader knows and can see your workflow. Okay. After all, whenever you're answering these questions over here, keep in mind that the final answer, yeah, that's worth 1 mark. So if this question's out of 5 marks, where did the rest of the 5 marks come from? It's from showing the reader how you got to the answer. In a sense, you're trying to give an exemplar, all right? So if someone is new at the stuff over here, you're trying to give an answer key where someone who's new at it can follow along with what you're going through, and then after staring at it, they say, oh, now I understand this concept and I can solve this on my own. And that's how you should be answering these questions when it comes to unit test time. 200 times cosine of 20, close, and we're done. 187.94. 187.94 kilometers per hour. Okay, and just to bold it out, now we have this vector and we have this vector, and we're just trying to solve for this arrow now, or this angle, as well as our big resultant vector. Okay, so I'll start for the magnitude first. So VPG squared using Pythagorean theorem is equal to VPGX squared. I'll color code it, why not? VPGX squared plus VPGY squared, because we have those. Okay, I'll stick with black and white from here because that's quite a bit of extra work. The minus sign doesn't really matter, but I'll just keep it in there just to maintain consistency. We know that negative times a negative will give us a positive. That's true. Why is that? I have a YouTube video on that, so if you have a chance, go check that out. Okay. So negative 148.40 kilometers per hour squared plus 187.94 kilometers per hour squared. Handy dandy calculator. Oh no, why aren't you working? There you go. Okay. Root of 148.4 squared plus 187.94 squared. I wasn't paying attention. Yeah, that should work out because the hypotenuse should be longer, 239.47. Okay. Last thing is the angle. So the angle of VPG, if we want to do that in green, sure. The angle of VPG is equal to the tan inverse of our opposite, which is VPG x divided by VPGY. At least that is according to our diagram here. I mean, some people might draw it the other way around, where you start off with the horizontal component first, finishing off with the vertical, and now you're looking for a different angle. Okay, and in that case over there, your terms would have flipped around. Okay, but I'm solving this according to the way how I drew this triangle up above. It doesn't matter which way you solve it, you're going to get the correct answer. It's just your relative bearing reference point is different. Okay, so that's equal to 10 to the negative 1 of 148.40 kilometers per hour divided by 187.94 kilometers per hour. Okay, again, we're treating this as scalar. I didn't put a vector sign on top, so the minus sign doesn't matter. If you're wondering why the minus sign exists and how it will affect your final answer, I guess if I make a video on that in the future I will, but right now we're basing upon this triangle here. Okay, so we know that we're going to deal with a positive angle here, not some other funny angle because of the cast rule. Okay, so calculator out, and we see that because these two are almost the same answer, we know our final answer should be roughly around 45 degrees, maybe slightly less. Come on, there's the calculator. Are you going to work? You're going to, can't use the word crash in the world of Apple, just failed to respond. Okay, tan inverse of 148.4 divided by 187.94, and that should give us slightly less than 45 degrees. Sure, 38.29. So 38.30 if you round to 2 sig fig. Okay, so as our final answer, VPG as a vector, that's equal to 200 and 2 sig fig, 2.4 times 10 to the 2 kilometers per hour, north 38 degrees towards the west. And if for some reason on my answer key I wrote that out in meters per second, then you would just simply take, why this is not working? There you go. Your 239.47 and divide that by 3.6 to get your 66.5, which is why I have 67 if that's what it is on the answer key. Okay, no big deal. As long as you include the correct units, I'll just write this down for good measure, 67 meters per second, then yeah, they're both correct. Okay. I wouldn't take any one over precedence over the other unless the question says state your final answer in kilometers per hour or meters per second. Okay. These two are both correct. There's no difference in them. Okay, moving on to the next day's question. All right, pilot with a heading of north 30 degrees east and an airspeed of 400 kilometers per hour flies into the wind coming from the north. In other words, this is flying towards the south, as we described from before. What is the plane's velocity relative to the ground? So let's go off and connect these together. Right, we know that VPG, if I write this out, VPG is equal to VPW plus VWG. Remember that this is my resultant vector. I'll just write that out bold. Okay, so that's vector number 1, that's vector number 2, and here's our bold vector. Okay, and you can solve this using whatever method that you want. Since the previous one I solved using the component method, how about I solve this one using the trigonometric method? In that case, we just want to label our vertices. I'll just call that C, I'll call this A, I'll call this B. If you're wondering why did I choose this order over here, well, I know that, for example, when I use the cosine law, it's always written out in our heads as c squared is equal to a squared plus b squared minus 2ab times cosine c. At least that's what we learned back in grade 10. So, keeping to that setup, since this is our answer we're trying to solve for, that's why I decided to call the opposite side C, and over here. Yeah, C for side C. That's why I chose that. As for the other two, it doesn't really matter. You can call this A or the one down below A. It don't matter. Just make sure that if you try solving this, if you're trying to solve this using the trigonometric method, make sure you label your vertices so the reader knows how to follow along with all your calculations. Okay. Again, you want to set up your answer as an exemplar so that those that are new to this can follow along and figure out what's going on. Okay, so a squared is PW, which is our 400 kilometers per hour squared, plus our 110 kilometers per hour squared, minus 2 times 400 kilometers per hour times our 110 kilometers per hour times the cosine of angle C, which is the angle up here. And have we figured that out yet? Oh yeah, we got to start solving this by knowing what's going on. So VPW is at north 30 degrees towards the east, and VWG is just directly facing towards the south. So we look at this as a bigger picture, we're just using the Z pattern in solving out angle C. So we can state that angle C is equal to 30 degrees by using the Z pattern. Okay, so that's how I knew that cosine is equal to 30 degrees. I guess this is one of the simpler problems, but they will get more complicated in trying to find the answer. Now, if you're wondering, why did I write this stuff down? Some physics teachers care, others they don't. I am a stickler for it because of the stories I've talked about earlier in this course. If you don't include units, the reader has no idea what you're talking about, and there are many disasters that happen because people made an assumption. All right, they weren't sure if it was in meters per hour or kilometers per hour. They took a guess without verifying it with the previous mathematician or engineer, and disasters have occurred. So please always include your units. Right? Otherwise, a person will not know what you're trying to get at. Okay, so the root of 400 squared plus 110 squared minus 2 times 400 times 110 times the cosine of 30, close bracket, and close bracket for good measure, and that will tell us side C's length. So 309.66. Good. Next thing we got to figure out is what exactly is this angle. Well, actually, not that one. This entire angle here relative to north. To get there, we have to add 30 degrees with mystery angle B. So we got to find out what angle B is. Well, we know that from the sine law, sine of capital B over lowercase b is equal to sine of something over something. Okay, we'd either choose sine of A over little a or sine of C over little c. Since we don't have all the details for A, because we just solved for C, then yeah, that's the process of elimination. Okay, so we didn't need that sine A over A. Just go straight to is equal to sine C over C. Isolating for angle B, we have angle B is equal to the sine inverse of B times sine capital C over lowercase c. Yeah, that's right. Through enough practice, you'll be able to rearrange these things in your head. Okay, little b is equal to WG, which is 110 kilometers per hour, times the sine of, and I hope we carried enough sig fig. Yeah, we did. 30 for there, and 309.66 km per hour down here. And just for a bit of logic, you'll see that these two have to divide each other out, because as I said, with regards to sine, cosine, or tangent, it doesn't care about units. It only cares about ratios. So the units have to divide each other out. All right. So if you mix these units up with kilometers per hour on top and meters per second down below, you're not going to get the right answer. Okay. So make sure they're the same unit. Doesn't matter which one it is, as long as they're the same. Everything else will work out in your favor. calculator time, so a shift sine of 110 times the sine of 30. Watch out, this one has already open bracketed for you for the sine, so close bracket that one. Divided by 309.66, close bracket, equals 10 degrees. Was it 10.23? Yeah, 10.23 degrees, just in case if we need it. Okay, remember that this 10.23 is just for that little angle up there. Okay, so if we really want to find out the angle of VPG, that's equal to 30 degrees plus angle B. Tell the reader how you got to your answer. Okay, so that's equal to 30 degrees plus 10.23 degrees, which gives you 40.23 degrees. Therefore, your final answer of VPG as a vector is equal to 310 kilometers per hour. If you want to write that down as significant figures, proper significant figures, then 3.1 times 10 to the 2 kilometers per hour. And from our reference, we're going north towards the east. All right, so north 40 degrees towards the east. I see on the answer key I did east to the north, so really it's 3.1 times 10 to the 2 kilometers per hour east, 50 degrees towards the north. Again, it doesn't matter, they're both correct answers. Okay. Take either one of them, they're both fine. Okay, there's a boat seen from the land moving at this, so that's why I have it nice and bold. This is our final answer. This we cannot choose. We cannot change. We do notice, and if you want to sketch this out in the corner, you're more than welcome to. Okay, the water is traveling towards the south. So the only way we can get this as our final answer is if we overcompensate and try to fight against the water current. Probably not that way, but most likely this way. So that when we lose against the water current, it gets us to our resultant vector. Okay, so we want to draw it something like this. We try really hard to compensate for the water flow, and that gets us to X marks the spot. I'm sure when I animate this out, it gives me the same exact answer. Okay, so that's our setup. Okay, so with our setup here, let's see what we know so far. VBG, we do know that, so this answer we know. VWG we know, and VG is traveling at north 29 degrees towards the west. So if we use the super Z, we know that in here it is also 29 degrees as well. What can that tell us? Oh, no. Is that helpful? No, that doesn't help us. We want to know this angle here. Okay, yeah, sorry about that. I'm just thinking out aloud. Here is our Z. Okay, because VBG is facing north 29 degrees towards the west. And if we use our big highlighter just for the Z pattern, this is the Z pattern I'm looking for. We know that this angle out here is also 29 degrees. So if we know that is true, then this angle over here would be equal to, what do I call this? I'll call this C, A, and B. Then angle B is equal to 180 degrees, subtract 29 degrees, which gives us 151 degrees. And that's solved by using the Z pattern. And you could call it, and supplementary angle theorem. Okay, that's how we found out the 151 degrees. So angle B is at 151 degrees. These type of questions are probably a whole lot easier solving using the trig method than the component method. All right. Okay, so we know that's 150 degrees. We have side, angle, side. Hey, what do we know? Side, angle, side. And in that case over here, just to make our lives easier, I'm going to call this C and flip that with B and call that angle C. Again, the reason for that is because we're so brainwashed into writing out the formula like this. C squared is equal to A squared plus B squared minus 2AB times cosine C that, hey, if you've memorized it that way, then why not just set up your nomenclature so that works out in your favor. Okay, so our VBW does work out to side length C. Okay, so root that for the value of C, and that's equal to A squared, which is WG, which is at 5.0 kilometers per hour squared, plus 15 kilometers per hour squared, minus 2 times 5 kilometers per hour times 15 kilometers per hour times the cosine of 151 degrees. Calculator time. .52 kilometers per hour. Good. Now we found out the length of VBW. To solve for the angle, remember that 29 degrees came from relative to north. Okay, so we have to figure out what this little angle is right over here, and that corresponds to angle A. So let's solve for angle A now. Okay, since we have the pairs of angle C and side length C, we know that sine of capital A over little a is equal to sine of capital C over lowercase c. So angle A is equal to the sine inverse of A times sine capital C over lowercase c. Okay, capitals for angles, lowercase for side lengths. Little a is WG, which is at 5.0 kilometers per hour times the sine of 151 degrees divided by 19.52 kilometers per hour. .13. Okay, so again, to find out what your VBW is, right over here, that's your angle of VBW. We got to take out our angle of VBG and subtract it from angle A. All right, so we need to take the 29 degrees and subtract it from 7.13 degrees. So 21.9, subtract the answer if you trust that on your calculator, and we get 21.87. So therefore VBW as a vector is equal to 20 kilometers per hour, and this is north 22 degrees towards the west. Okay, if the passengers wish to get to a point 790 meters away in this direction over here, so that's 790 meters away, and we already know how fast the boat is traveling, how long will it take? So with that last part, I wish I was a bit more organized. Yeah, just to keep everything on the same screen, I'm going to fill in the rest over here. We know that D is equal to V delta T. So delta T is equal to delta D over V. So 700, I guess that'll part of the givens. Delta D is equal to 790 meters. So 790 meters divided by V, should be more specific, VBW. There you go. Okay, of, meters, kilometers per hour. Okay, what I probably want to do is to make sure the units are consistent. So first thing I got to do is convert the 19.52. So VBW is equal to 19.52 kilometers per hour. And you know what? We, as physicists, generally know that whenever you divide by 3.6, you convert into meters per second. So just have that shown somewhere so that the person knows how you got around to that. So 19.52 divided by 3.6 will give us 5.422. So 5.422 meters per second, because we need that. 5.422 meters per second. So 790 divided by 5.422 will give us 145 seconds. Oh, 146 seconds. 145.7. How about that? 5.7 seconds. And since the question never really asks how long will it take in whatever unit, you could leave it as this, written scientific notation, which would be, 1.5 times 10 to the 2 seconds. But to the average person, they have no idea what that means. Okay, so even though it is mathematically correct, you probably want to write it down in some unit that a person can comprehend. And you know that there are 60 seconds per minute. Okay, so what you want to do is you want to do your 145.7 divided by 60, and that will tell you that it'll take a different answer. So what mistake did I make? Oh, where did I go wrong? Did I type it in wrong? 790, oops, divided by 5.422 divided by 60 seconds, 2.42 minutes. Seen from land, I am so terrible. Okay, I am doing this stuff real time. This is boat to water. What's wrong with me? I need boat to ground. Ay, ay, ay. Boat to ground. Okay, that was my mistake. I apologize. Because someone's seen on land, so you want the boat to ground, and you've already been given that answer. So 790 meters, because after all, this is boat to ground as well. All right, the distance of 790 away, the boat from land. So we need to divide by boat to ground of, let's just do this calculation here, okay? Velocity of boat to ground is equal to 15 kilometers per hour divided by 3.6. I am doing all this stuff real time, so if I'm making mistakes, I apologize, and to be honest with you, and maybe you'll see the same mistakes that you might have made. I'm just going to keep everything as is. Sorry for a long video. 15 divided by 3.6 will give you 4.167 meters per second. Okay. Sorry, I'm running out of space here. Otherwise, I would have made this a lot more linear. So 4.167 meters per second. And now when we take out our calculator, we have 790 divided by 4.167, and we get 189.58 seconds. So 189.58 seconds, which 190 seconds would suffice. Again, what does 190 represent? Most of us don't know, so that's why we want to divide that by 60 seconds, and that will give us our 3 minutes and change. Okay, so our 3.2 minutes. There you go. Okay, so you could either answer this as 1.9 times 10 to the 2 seconds or 3.2 minutes, but as I said, for comprehension, you probably want to switch over to minutes, and if you do it in hours, it's in a fraction. It's hard to read as well. Okay, a large man wants to fly east. So we know that this is our final vector. Okay, so this cannot be changed, undisputable. He's able to fly at 26 kilometers per hour, and we don't know which way he's going to fly yet. But we do know that he needs to fight against the wind, right? And the wind is blowing towards the southeast, like so. And I'm going to color code everything because I think that helps. Okay, where's the blue wind? There you go. Blue wind is blowing towards south 20 degrees east. So if we want him to be able to fly east, we know that he needs to try and angle himself like so. Okay, he needs to direct himself towards the north so that when he gets pushed by the wind blowing south 20 degrees east, he gets to where he needs to get to. And that's how we set up the structure for this diagram over here. There you go, all animated out. Okay, so we know that he wants to fly east, so we know the vector for this is going to be east, and that's all we know here. Man to the wind, we know that it's at 26 kilometers per hour, but the angle we have no idea yet. The only thing that we do know for sure is this value over here. You can solve this problem either by using component method or trig method. If you try the component method, I believe this is one of the nightmare questions, so don't use component, use trig instead. And I'll explain why it's a nightmare at the end with another example. Okay, but in this question over here is far easier to solve by using the trig method. Okay, what do we know so far? We know that since this is at, was it 20 degrees? Yeah, south 20 degrees towards the east. What else can we find out? Oh, we know that by the Z pattern over here, let me just highlight it out for those to see. We know that over here, this is also 20 degrees. If that's the case, then this angle over here would be the complementary angle. What shall I call everything? Sure, I'll just stick with C over here, A here, and B over here. So we know that angle B is equal to 90 degrees, subtract 20 degrees. Okay, and that's because that's the complementary angle. After all, this vector over here is going east-west, and this is facing north-south, so that's 90 degrees. So the complementary angle of 20 degrees is equal to 70 degrees. Okay, make sure that you describe to the reader how you got to this. Okay, so there is one mark for this. Okay, telling the reader how you got to angle B. Okay, so now that we know that this is at 70 degrees, what else do we know? Let me just remove all the other things because they get messy. Okay, so we know that's at 70 degrees. I'm just going to highlight what we know. We know that MW, the magnitude, and we know that WG, magnitude. And right off the bat, I see that I have a side and angle. Anytime that you have a side and corresponding angle, you can use the sine law to solve for almost everything else, as long as you know some other information. For example, A. Okay, we know A's side length. So that's how I figure out that to solve this, I probably just need sine of A over A is equal to sine of C over C. And we're just looking for angle A. All right, so angle A is equal to sine inverse of little a times sine of capital C over C. Little a is VWG, which is at 10 kilometers per hour, times the sine of, oh, not C, B, sorry, sine of B over B. Have it. Sorry about that. Okay, we have B's pair. Okay, so sine of B, which is at 70 degrees, over side length B, which is man to the wind of 26 kilometers per hour. Some might be wondering, do we need to convert this to meters per second first? No. As long as the units are the same, they will divide out in your favor at the end after all. Okay, so don't worry too much about what unit you should be using. Just make sure they're consistent. That's the most important part. Calculator time, shift sine, 10 times the sine of 70, close bracket, divided by 26, close bracket, and that will give us 21.9 degrees. 21.19 degrees. Okay, so what angle should the man be flapping at? Which is this angle over here, VMW. So this is also equal to angle of VMW. Luckily for us, because VMG is facing towards the east, we know that angle of VMW is just simply equal to angle A plus 0 degrees, right? Because MG is already facing towards the east, and that's why it's still 21.19 degrees, and that's what is it, east, 21.19 degrees towards the north. Okay, so you should flap his arms eastwards 21.19 degrees. Yep, toward, so that when he gets fought by the wind, he's facing east at the end of the day. Okay, since he's fighting against the wind, his overall ground speed will change. Luckily, if you take a look at WG, it's in favor, right? It's allowing him to travel a bit faster, and that's why the green vector is longer than MW. Okay, so how do we find out that side length over to here? Whoops, over here. Let's just pull out a bit of elementary school trigonometry. All right, we know that we have a big triangle over here, and according to SATT, we know that angle A plus angle B plus angle C will equal to a total of, you're right, 180 degrees. Okay, so if we need to find out angle C is equal to 180 degrees, subtract angle A, subtract angle B. So 180 subtract, I know I'm going to run out of space, and I'm sorry about that. 180 degrees subtract angle A of 21.19 degrees, subtract angle B of 70 degrees will give us 88.81 degrees. Okay, so we know angle C, and how are we going to solve for this? Sine law. I would just use sine law, and since I'm running out of space, I'll just write out here angle B is equal to 90 degrees, subtract, what was it, 20 degrees, which will equal 70 degrees, and this is due to complementary angle theorem. There you go for that 1 mark. Okay, so the last part is sine C over C is equal to sine of, I would use B over B since those are less rounded, those answers. So sine B over B. Of course, if you're pressed for time on a test and you use A, as long as your answer is correct, it will work out. Just make sure you carry extra sig fig. Okay, we need to find out side length C. So side length C is equal to sine B. Wait, no. I don't do this one as often. So sine C over sine B times B on top. There you go. Yeah, bring that up, bring that up, bring that down, and that's what it'll look like. Goody. Okay, so B is equal to VMW, so he's able to fly at 26 kilometers per hour times the sine of 88.81 degrees divided by sine of 70 degrees. 26 times sine of 88.81, which is very close to 90, by the way. So that's why if you accidentally treat it as a right angle triangle, you'll get close to the right answer, although that's the wrong approach of solving this. Divided by sine of 70 degrees, close bracket, and you get 27.66 kilometers per hour, and that is how fast his land speed is. So this is velocity of the man to the ground. Again, he was traveling in the east. We knew that already. And that is our final answer, 28 kilometers per hour when you round. Okay, which is equal to, I'm running out of space, 28 kilometers per hour towards the east. And we're done. Okay, question number 10. A motorized canoe is pointing north 20 degrees west, so that's its speed relative to the medium, but it's noticed that it's been traveling this way. Okay, so it's trying to go this way, but it ends up going that way, and the question is, how is the river influencing it? And you know the river logically must have been pushing it this way to make it get there. Okay, and that's the river to the ground. Okay, so that's the setup. Okay, we know that the boat is seen moving at 7.6 meters per second north from ground. That's our resultant vector, and you know that you need to add the first vector with the second vector to get to your end conclusion. After all, it needs to abide by the formula, right? Where adjacent subscript letters are the same, and whatever that's left over describes the big picture at the end of the day. This is the big picture, and that's equal to CR plus RG. Okay, so that's the check. Okay, I'm just going to highlight what I know so far. CR, we know this as well as the angle, which helps, and we know CG. So what is that? Side angle side? Yeah, cosine law. Okay, let's label out the vertices. Probably call this C just to make our lives easier. Okay, because we know that C squared is equal to, I'll write it higher, C squared is equal to A squared plus B squared minus 2AB times cosine of angle C. Sometimes, just to be grammatically clear, because some people can't see the difference between capital and lowercase, you could do angle C. Okay, just for clarity's sake. That's equal to the root of little a, which is CG, which is 7.6 meters per second squared, plus b squared, which is CR, and that's why you want to draw your diagram, right? Because the diagram allows the reader to follow along and see where you're getting everything from. So b is 5.0 meters per second, and yeah, that's why you have given 2, all right? So we can cross-reference everything. Squared minus 2 times 7.6 meters per second times 5.0 meters per second, close bracket, times the cosine of angle C, which is north 20 degrees towards the west. So cosine of 20 degrees. Pull out our handy-dandy calculator, and the root of 7.6 squared plus 5 squared minus 2 times 7. Whoops, something typed out wrong. 2 times 7.6 times 5 times the cosine of 20 degrees is equal to 3.368 meters per second. Okay, so that's the river current's speed. As for the angle, you could solve for angle A, but you'll notice that that kind of looks greater than 90 degrees, doesn't it? All right, and if you've already taken it in math class, you'll notice that there are these exceptionality calculations. All right, so whenever you have obtuse angles, sometimes the trig rules don't work so well. So you can try it from that method. You notice you get the wrong answer, and you have to do 180 degrees, subtract whatever your calculator gets to get to angle A. Or better yet, here's an easier approach. All right, we know that CG is facing towards the north. So if we take a look at it, this angle over here is equal to angle B, right, according to using the Z pattern. All right, so let's state that verbally. Okay, so the angle of VRG is equal to angle B by using the Z pattern. Okay, so let's solve for what angle B is. Taking a look, what do we have so far? Okay, we have 20 degrees over here, and we have RG. Oh yeah, so we can just use sine law, right? So sine and sine, good. Okay, so sine of B over B is equal to that pair of sine capital C over lowercase c. So angle B is equal to the sine inverse of little b times sine of capital C over lowercase c. Little b is VCR, which is at 5.0 meters per second, times the sine of 20 degrees, divided by little c, which is RG, of 3.368 meters per second. Make sure units are consistent, and let's go and calculate that out. Shift sine of 5 times sine of 20, close bracket, divided by 3.368 is equal to 30.5 degrees. Okay, and that works out to an angle of VRG. So therefore, VRG as a vector is equal to 2 sig fig 3.4 meters per second north 31 degrees towards the east. All done. Oh, I forgot about the animation. Yeah, you could also use the complementary rule and flip them around. And once you flip them around, then you're just looking for this angle over here, and that's another way to avoid dealing with the exceptionality rule, right, of obtuse angles. Toucan Sam decides to fly his 3 nephews, and what does he know? They are located north 30 degrees east of his house. Okay, remember that this is kilometers, not kilometers per hour, so we don't know the velocity of this, but we know that this is definitely facing north 30 degrees towards the east. Okay, that night the wind was coming from where? Well, blowing towards the south, so we have this huge gust of wind blowing towards the south. Alright, So the only way that he can end up at his destination is if he flaps his wings ridiculously hard, overcoming the wind current. All right, so your triangle would look something like this. There you go. Okay, so he has to flap crazy hard so that when the wind finally blows in towards the south, he can travel in the direction as intended. So that's the setup. Okay. Yeah, we'll label our vertices first. I don't know. I'll just start off with this. I don't know if this is the best, but we'll go with that and work from there. Okay. What do we know so far? We know that this is at 30 degrees. What does that tell us? If we use the Z pattern, then we know angle B already. Okay. So we know that angle B will be equal to 180 degrees subtract angle VTG. So 180 degrees subtract 30 degrees, which will give us 150 degrees, and this is because of the supplementary angle theorem and the Z pattern. Okay, remember that this is 1 mark. Okay, so make sure you show how you got to that. Okay, so angle B we know, VTW we know as well. Hey, if we know these two, then sine law, done. Okay, so sine of B over B is equal to whatever else we're trying to solve. Since we know VWG, that means that we can pair it off with our sine A over little a. And since little a is what we're trying to solve for, do we? No, we already know a. That will solve us for this angle over here. What am I doing? Let me go back again. I don't know this part. And I'm trying to solve for this angle here. Yes, I am. So shouldn't I be solving for angle C? Do I know this length here? No, I don't, but I know that, so I can solve for angle A. Yeah, so we're solving for angle A first. That's right. Okay, so we're going to solve for angle A first, and then with angle A, we can eventually solve for angle C. Okay, so we're going to solve for the useless before we solve for the useful. So yeah, I am doing things as the next logical step because there's no other move I can make in the game of this kind of chess. Okay, so yeah, we solve for side length A. No, angle A. Yeah, angle A is equal to sine inverse of little a times sine of B over B. I mean, if you're a bit confused right now, I hope that'll make more sense as I go along through this, because I don't have any other chess moves right now that I can perform. Okay. So little a is WG, and I didn't state that in my givens. Oh, naughty me. I didn't have that. That's why it's so confusing right now. So, out of good habit, I'll write that down over here. What are my givens? I know that velocity of, angle of VTG is equal to north 30 degrees east. That I know. Velocity of Toucan Sam to the wind is equal to 8.0 meters per second. Direction we don't know yet. And we know that velocity of the wind to the ground is at 6.00 meters per second towards the south. Okay, we should have created that given legend at first, okay, because that helps us solving everything else. WG we do have, because WG is at 6.00 meters per second times the sine of angle B, which is at 150 degrees, divided by little b, which is TW, which we do have as well. And this is the only move that we can make, which doesn't seem to make any sense now, but I hope it'll make sense after we complete this. So shift sine of 6 times the sine of 150, close bracket, divided by 8, close bracket, and that will tell us that the angle A needs to be at 22.02 degrees. Which, yeah, is fine and dandy. That means that this is equal to 22.02. But because we're solving for VTG, and I'll just do that in green, okay, since we're solving for VTG, we need to know this angle here. So that's why we need to solve for angle A, because angle C can be solved by doing 180 degrees, subtract angle A, subtract angle B. Right, so that's using the sum of angle triangle theorem. That's why it's SATT. Okay. So 180 degrees, subtract angle A of 22.02 degrees, subtract 150 degrees will give us 7.98. degrees. And with that, we can figure out VTG. Okay, so sine of capital C over lowercase c, and this is what we're trying to solve for. Yeah, we're trying to solve for that. That is equal to another pair that we have, which is, which one's the least mucked around with? I'd say B. Sine of B over little b. Okay, so little c is equal to b times sine of capital C over sine of capital B. So little b is TW of 8.00 meters per second times the sine of angle C of 7.98 degrees divided by sine of angle B, which is 150 degrees. Calculator time. Come on, calculator. No, you're not going to come out, are you? There you go. Eight times sine of 7.98 close bracket divided by sine of 150 close bracket for good measure, and that gives us 2.22 meters per second. Okay, and now we find out VTG. Okay, so yeah, I could do therefore VTG, how he's really flying at is not very quick. He's only traveling at 2.22 meters per second north 30 degrees towards the east. Okay. Oh, we're trying to look for this angle here. Whoopsie daisy, I kind of jumped ahead. We got to figure out how he must direct himself. So yeah, this part over here will help us figure out what angle he must direct himself at, right? Because we're trying to look for different color. How about this? VTW. Okay. We're trying to solve for angle of VTW is equal to 30 degrees subtract angle A. Okay, so 30 degrees subtract 22.02 degrees will give us 7.98 degrees. So therefore, the angle that Toucan Sam, or it was an angle, yeah, it's only asking for the angle. Angle of VTW must travel at is equal to north 7.98, which is right over here, if you're wondering. Okay, that's why it's 30 subtract 22.02. North 7 point, I guess 2 sig fig, north 8.0 degrees towards the east. So sorry, I kind of jumped ahead and missed out on part A. Okay, so that's the angle. And what is his velocity? We did that already. And the last one is how long will it take for him to get to his end destination? Okay, and we're given that hint right up here. That's his distance. Okay, so if you want me to clean it up a bit, in our givens, we know that our delta D is equal to 2 kilometers. We're just going to maintain a consistent unit here, 2,000 meters. And we already know that TG, or his velocity, is equal to 2.22. Oh, I should carry one more sig fig, right? No, yeah, I'll just do that calculation one more time. Oh, I have it here, 2.221, just for good measure. There you go. 1 meters per second. So then our delta T is equal to delta D over V. So 2,000 meters divided by 2.221 meters per second. Calculator time. $900 seconds. Again, 900 seconds, if you want to leave it as is, or 9.0 times 10 to the 2 seconds, go ahead, that's fine. But if you want to be able to comprehend what that means, you know, to a regular human being, you probably want to divide that by 3.6. And what happens? Oh, not 3.6, multiplied by 0.6, divided by 60 seconds, sorry. Because it's in seconds, divided by 60 seconds will tell you that it's equal to 15 minutes. And that's how long it'll take for him to fly. Oh, things didn't capture properly all this time. I just noticed that right now. Oh, come on, program. Why so difficult? I should have paid attention to that before recording. That took me long enough, so I'm just gonna let this be as is. Sorry about that. I hope that me verbally explaining things kind of filled in the blanks. I really apologize. I missed out on that at the beginning. Okay, moving on. An airplane intending to fly at 200 kilometers east, 30 degrees north, so I'll just draw that vector first, ends up flying at 180 kilometers north, 30 degrees east. So that's my resultant vector. Okay, so it tried to go this way, but somehow something pushed it, so it reached over there. And that would be the corresponding wind to the ground. And that's the setup. Okay, so formula first. Formula's always good. Okay, VPG, which is our resultant vector, is equal to number 1 plus number 2. Connect them from head to tail, and yep, the laws of vectors is valid here. Okay, we abided by it, and that's how we set it up. Noticing that the relationship over here is that this must be another 30 degrees. Okay, because yeah, let's just label this out. A, B, and C, for I do not know what I'm going to use yet. I'll just let that be. We first want to tell the reader that angle A is equal to 90 degrees. Subtract the angle of VPG, subtract the angle of VPW, which is 90 degrees, subtract 30 degrees, subtract 30 degrees, which is equal to 30 degrees. Again, show this for that one mark. Okay, how did you get to that? With that, let me just highlight what we know. We know that angle here, we know VPW, and we know VPG. Side angle side, cosine law, and that means that I'm glad that I can erase this because I probably want to call this angle C down here. And maybe flip that to angle A and call that angle C. Yeah, that's all I need to do. Again, sometimes we just want to stick with the brain dead, so c squared is equal to a squared plus b squared minus 2ab times cosine c. I mean, if you do want to flip the formula around, by all means, it will still work out. Okay, just make sure you label all your vertices correctly according to the question. Okay, so the roots of, I hope I have the space, I'll just write it over here. I apologize. Equal signs should all be lined up vertically. Okay, you should abide by that. And you know what? I'll just do that. Why not? Minus 2ab times cosine of c. And that's equal to a squared, which is VPG, which is 180 kilometers per hour, squared, plus 200 kilometers per hour squared minus 2 times 180 times 200 times the cosine of c, which is 30 degrees. To 0.23, so 100.23 kilometers per hour, and we're trying to figure out the velocity. All right, so not only just the 100 kilometers per hour, we need to know the angle. And here's where things get interesting. How can we figure that out? I'm going to start off by looking at the not so obvious Z pattern over here. Okay, let's seems rather thick, so I'm just going to draw it out in a different color. Okay, so these two lines are parallel with each other. So if you know that's 30 degrees down here, then this must also be 30 degrees. Okay, so we solve for angle A, and we do A subtract 30 degrees, then we can find out this tiny little angle here, which corresponds to the angle of VWG. Okay, so we got to find out angle A first, so let's work through that. Probably sine law, trusting that it'll work out, is equal to sine C over lowercase c. So A is equal to the sine inverse of A times sine capital C over lowercase c, sine to the -1 of little a. Where's little a? Little a is VPG of 180 kilometers per hour times sine of C of 30 degrees divided by C. Where's C? C is WG. Yeah, 100.23 kilometers per hour. Sorry, sometimes I do things by instinct because you can see it's more or less the same process over and over again when you're solving for it. You're just doing chess moves until you can fill in all the blanks. Or Sudoku if you want to think about it that way. Okay, where's the calculator? There it is. 100, whoops. Shift sine of 180 times, you could do 0.5 if you're brave. I'll just do that, okay, because sine of 30 is 0.5, divided by 100.23 will give you 63.88 degrees. Okay. However, if you're trying to look for angle VWG, that's equal to angle A subtract, or theta, sorry, theta subtract angle A. Theta, no, A. Angle A subtract 30 degrees. Okay, so 63.88 degrees subtract 30 degrees will give you 33.88 degrees. Okay, so therefore VWG as a vector is equal to 100 kilometers per hour, and from the west, right, because we're doing west angle up to the north, so west 34 degrees towards the north, and that should match up with the answer key. Yes, it does. Is it number, okay, before I finish off, you know what, I'm just going to rewind everything so that you can see the answers for all of these, because I just realized that things were cropped off, and I apologize for that. I probably have to crop the video before I post it online. So come on, keep on going, keep on going, keep on going, keep on going, keep on going. Okay, so here's the screen capture for number 1. Here's a screen capture for number 2 for whatever I got left of it. Here's 3. Yeah, 3. Here's 4. Question 5. Question 6. Question, oh, just that part? I hope you get, yeah, that should have made it through. Question 7 with all the scribbles. Question 8 with all the scribbles. Question 9 with all the scribbles. Question 10, wait, is that, oh, there you go. Question 9 with all the scribbles. Question 10 with all the necessary stuff. Oh, that would have cleared. 11, here you go, one more time. And I think everything else is visible now. Alright, so we got through everything, and I apologize for messing it up. Okay, so let's just go back to this question one more time from the previous day. When we solved this, we solved it by using the trigonometric method, and you can see that I could solve everything in one PowerPoint slide. Done. Alright, but let's say you decided to be brave and solve this by using the component method, and here's where things start to get really, really dark. Okay, if you want to solve the same exact problem using the component method, well, now you got to take the diagram that you just drew and break it down into all of its components. And now you need to create equations to describe each dimension. All right. So first off, making sure the formula is correct. So the w's are beside each other. That's good. Leftover letters describe the formula. That's good. Is this our resultant vector? Is that equal to vector 1 plus vector number 2? Yes, it does. So the picture is correct, the formula is correct, and now let's start solving from its components. Here's the problem. VBG, we know the angle, but we do not know the length whatsoever. So we've already incorporated a variable right over here. That's already one unknown. Okay. If we assume that towards the east is positive, then the components of VBW need to be negative. We don't know the angle yet, so that's why we have another variable in the equation. The only thing we know completely is this red vector up here. That's equal to the magnitude times the opposite of the angle, so the sine of 15. Okay, so here's our first formula. Okay, if you do it super carefully. Okay, negative as in we know the final vector points towards the left or towards the west. So you got to be very careful when you lay out the equation. If you have a sign that's incorrectly written out, things are going to go down under. On top of that, this is an equation with two unknowns. As you can probably guess, if you have an equation with two unknowns, you probably have to create another equation and solve the two systems of equations. So we move on to the y dimension, and we have the same issue again. Okay, VBG, we may know the angle, but we don't know the length, so we're stuck with another variable. Okay, we don't know VBG, but we do know that the vertical component is equal to adjacent. Okay, so the cosine of 74 degrees. As for the purple vector, this part over here, we don't know the height, but we know it's equal to VBW times whatever the sine of it is, as that is the opposite side. Okay, so 40.22 times another mystery meat. Okay, another unknown variable. The only thing that we do know is solving for this little blue part up here, okay, which is equal to the hypotenuse of 2.7 times the adjacent, or the cosine of 15 degrees. So two equations with two unknowns. Doesn't sound too bad, but mind you, this one's locked by sine and this one's locked by cosine, and that's where the torture begins. Okay. So what did I do here? Yeah, I subbed in the VBG here into the equation up there, and I ended up getting this big, huge, ugly looking thing up here, which I need to simplify. Okay. And if we take a look at it right now, we have theta over here and we have theta over here, and we got to bring both thetas to the same side of the equal sign. So we need to first expand and try to collect like terms, and while collecting like terms, well, we have a sine here and we have a cosine here, and all this stuff over here works out to a numerical answer anyways. It's just a number, all right, just with a lot of decimals. Okay, so how do we solve when we have a sine and a cosine? Well, oh yeah, I cleaned it up here with decimals. Okay, the only way you can work this out is by using one of the trig identity rules, which is sine squared theta plus cosine squared theta is equal to 1. All right, so if you isolate for cosine squared theta, that's equal to 1 minus sine squared theta, or cos of theta is equal to the root of 1 minus sine squared theta. I think that's what I did next. Yep, that's the exact move I did next. Okay, and yeah, so I got to this point over here, and anytime you have a square root, you got to somehow get rid of it by taking this term and bringing it over to the other side, and then squaring both sides. So that's what I did next. Brought that over, and then I had to square to get rid of the square root. That brings me up to here. And look at the terms we have now. We have a squared of an angle, and we have a linear of an angle, and we have a constant. Oh, let's bring this squared over to the other side as well, just to clean it up a bit more. There you go. Okay, so a squared, linear, constant, this whole thing's a constant, whoops, is equal to 0. Huh, look familiar? Doesn't it look familiar to ax squared plus bx plus c is equal to 0? Isn't it in this format? And since it is, we can probably now incorporate the lovely formula, okay, lovely quadratic formula, okay, where this time around it's, yeah, ax squared, which is the sine of theta as your squared, is equal to, that's your a component, that's your b component, that's your c component. Sub everything in and crunch it out, and here's where things get kind of messy, right? Because you have two roots, one is positive and one that is negative. On top of that, this is the sine of theta. So you really do end up with multiple possible answers. Okay, the negative ones are the ones you're probably going to negate, and you're left with your angle here. Fine and dandy. Good, good. All right, so it works out, but you can see all the torture that it takes just to get to the same exact answer that you could have spared yourself the torture by solving it using the trigonometric method. Okay, so that's why you're taught both methods in physics class, because sometimes one method is a lot more efficient than others, and usually in the world of relative velocity, which is our topic, for the most part, just stick with the trigonometric method, all right, because it will work out every single time, and it's most of the time the most efficient way. After all, you're just dealing with triangles, not quadrilaterals and other shapes, all right, where component method is a lot more efficient. Anyways, that's all there is in this video over here. I'll probably include links to and to talk about, like, for example, you know, why is it that what is it, -1 times -1 is equal to +1. All right, I do have a video on that. Probably add a link somewhere up there, or maybe a box over here, I don't know, something like that when I finally post this thing. And I'll catch you in class the next day. And that's why I like the stuff recorded, because in class it just burns an entire period just trying to give away the answer. So see you guys tomorrow, and have a beautiful evening.